So there was a comment from Rajesh saying, I wish MPI replaced inefficient communication by the user in the best available in the library if the resulting algorithm is the same. The problem is that MPI is a library. So, I mean, unfortunately, it is sort of doing that. When you call MPI send, it will pick MPI effectively bsend or MPI send, depending on what it thinks is more efficient. If you call MPI all reduce, it will do it in the most efficient way. The problem is MPI is a library, not a. If it were a compiler, it could look at your code and say that's stupid, but it isn't. So unfortunately, MPI does the best job it can with being a library. So unfortunately, replacing information call isn't enough. It needs to replace the calls. You know, there isn't a call by call basis. The code is very different. You couldn't replace an individual call. The logic is different. So you're absolutely right. It would be nice if MPI could do that, but because MPI is a library, it can't do that. But the party line in MPI is call neighbor all to all, and I'll do the best thing I can, and that actually works here. So the party line, the answer to your question is that's very difficult for MPI to do because it's only a library. However, is always use the highest level routine you can. Use all reduce, don't do it yourself. Use neighbor all to all, don't do it yourself. So the higher level you do that, the more freedom you give MPI, the more it's able to do what you'd like it to do. But MPI is hamstrung by being a library, not a compiler. Does that answer your question? It's a good point. So what I'm going to do now is do the final talk. I've not really left enough time to do the exercise, but you have access to Archer for the next day or so. So hopefully, if you're interested, you could do it in your spare time. I will try and pick the correct talk this time. Bit embarrassing last time. Okay. So hopefully I finally managed to get around to what I'm supposed to. Fine. So I'm going to talk about advanced collectives. So what I'm really going to do here is the motivation. Okay. The motivation is collectives are a key feature of MPI. They're much simpler to use than implementing your own operations. They're much faster than the DIY approach. Okay. And there is some flexibility in what processes take part. So if you want to do a collective on a subcommunicator, if you want to do a collective on only even processes or the processes in a column or a row, you can pass a subcommunicator. However, what if your data layout doesn't match the collective's pattern? What if your data type is not supported? So what I'm saying here is so the second point, what if your data type is not supported, is if I want to do an MPI or reduce on a derived type, a structure. You might, in your language, be it C++ or Fortran, have overloaded to find the addition operator on two structures on a new data type. But when you call MPI or reduce, MPI doesn't know about that. You can specify your own user-defined reduction operations. I say see later here, that's in a later talk, so I'm not going to cover that here, but just to say you can do that. So just like when you define a new data type in Fortran or C++, you can redefine what the addition operation means on, or define what the addition operation means on that derived data type, on that structure or derived type. If you could create an MPI derived type, you can tell MPI how to do reduction operations on it, for example. But the main issue is what happens if your data layout does not match the collective's pattern. And this really comes when you do multidimensional arrays. Everything's very, very simple. You do linear arrays, and that's why the call to MPI neighbor all to all was almost trivial in my Halo bench code, because the data was just linear buffers laid out in a line. In real programs, that's not true. What you want to send are often the extreme boundaries of 3D arrays, which are not contiguous blocks of data. So you need to, but you can solve that by using data types. So the canonical example I'm going to use, and hopefully this gives you enough information to then apply it to other collectives, is we have a 2D array distributed across a 2D process grid. And we want to use MPI gather to collect the data onto a single process. And people ask, this is a standard question you'll see 1,000 times on Stack Overflow. I have a 1D array distributed across a 1D process grid. I can use MPI gather to bring it back to a single process. But when I use gather with 2D, it doesn't work. So I'm using that as a motivating example to go through the subtleties of data types, but hopefully will allow you to understand enough to use them in your own, to generalize it to other routines. And so this is something you often want to do. At the end of a program, you want to use MPI gather to collect data onto a single process. I've told you this isn't particularly efficient, it's very common before performing serial I/O to disk. So I'll do this example in some detail. It's straightforward to generalize to other examples. I've got scatter, reduce all to all, but also the neighborhood collectives as well. The difficulty is really understanding how derived data types work with the collectives. After that, it's relatively easy to apply to other cases. Now, a lot of people just go and find this code on Stack Overflow and use it, but you do need to understand what's going on. So here's my canonical example. I've got a 2D array, okay, which is 4 by 4, which has 16 entries. 1, 2, 3. The way I've drawn it here, I've drawn it in this order. I mean, but anyway. So remember, there is no such thing as a 2D array, really. A 2D array is just a 1D array indexed in some way. C and Fortran disagree about how to index it, but what I'm saying is I have a 2D array which has 16 elements, and I imagine that they're ordered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've distributed this across a 2D grid of processes which are ranked 0, 0, 1, 0, 0, 1, and 1, 1. So that's a this is basically what my Halo Bench example did, except it was 3D arrays. So the problem here is that when I gather this to rank 0, what I want to do is this, okay? I want to end up with the same data layout. So if this were a serial program, okay, the serial array, a 4 by 4 serial array is numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. The problem is if I split it up in a 2D decomposition, the yellow process is responsible for elements 1, 2, 5, and 6. The problem is if I take a 2D array and split it up amongst processes, each process owns a contiguous 2D subsection of that array, but it is not, when you linearize that array, it's not a contiguous subsection of the global array. So the yellow process owns elements 1, 2, 5, and 6. The blue process 3, 4, 7, and 8. The red process 11, 12, 15, and 16. The green process 9, 10, 13, 14. So what I'm basically saying is, when you take a 2D array and split it up into 2D subsections, those 2D subsections are not contiguous blocks of the original array. They're scattered. Okay. So hopefully that's clear what's going on here. This is not a problem if I do a 1D decomposition. I could have split it up into slices here, in which case the first process would own elements 1, 2, 3, 4, the second one 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, everything would be okay. But in general, we want to do, for multidimensional arrays, multidimensional decompositions. So this is what I want to assume, I want to achieve. Of course, what's really happening is that there's no such thing as global indices. What's really happening is an MPI. Each process has a little 2D array which make up this big 4 by 4 array. And so this is the mapping. I want elements 1, 2 from the 0th process to go here, element 3, 4 here. This is what I want to do. It's just drawn that in a different way. So but really, again, of course, there is no such thing as a 2D array. MPI doesn't really understand. So what's really happened is rank 0 has 4 elements numbered 1, 2, 3, 4. Rank 1 has 4 elements numbered 1, 2, 3, 4. Rank 2 has 4 elements 1, 2, 3, 4. Rank 3 has 4 elements numbered 1, 2, 3, 4. And they want to be gathered together, reassembled in this order. Okay, so we can see that the elements from rank 0 are not received contiguously in rank, but they're scattered. Now, of course, we could do this by hand with sends and receives and copies, but we want to do this with a single collective. Why do we want to do it with a single collective? Because the collectives are very highly optimized. So a gather, and it's not really true with gather, but definitely with the all-to-all, they're very highly optimized. So we want to. So how can we shoehorn our collective to do what we want? If we just call the MPI gather, okay, so this is MPI gather. You have a send buff, a send count, and a send type, a receive buff, a receive count, a receive type, and a root. So the root, all processes in COM send count items of type send type from send buff to root, and the root process only receives receive count items of type receive type separately from each process. These are received into receive buff in rank order. Okay, and so what happens is, if you just did an MPI gather of this data, the first 4 elements from rank 0 would go here, the second 4 from rank 1 here, the third 4 from rank 2 would here, and the final 4 from rank 3 would go here. It would just receive them in rank order, which seems fine, but that's not what we want. We want to receive them like this in a more complicated order. So if we just call MPI gather by default, okay, then we're going to get the wrong answer, because they're just going to be placed here. Now you might, this is where it gets a bit technical, but if I do, so I'm doing send type equals receive type equals MPI int, and send equals receive count equals 4 in the gather call, if you're familiar with how gather works. You might ask, how does it know where to place the data from rank 1? Well, what it does is it places it at the rank, the displacement is the rank times the receive count times the extent of the receive type. What I'm saying is that the data from rank 1 is received at 1 times the receive count, which is 4, times the size of the data type, which is size of int. So the data from rank 1 is received at 16 bytes in the way. The data from rank, this might still seem overkill here, but this is what this will generalize. The data from rank 2 is received at offset 32 bytes, which is there. The data from rank 3 is received at offset 3 times 4 times 4, 12 times 48 bytes, okay, here. So that is how it does it, and that does this pattern that's well defined, but it's not what we want. So how can we not receive in that order, but receive like this? Or send, but I'm doing the receive as an example. Well, the first thing is, the first problem is the data pattern on the receive side is incorrect. The incoming messages need to be scattered into the receive buffer, okay? So the solution is to specify a vector or a subarray for the receive type. What MPI data types, vectors or subarrays, can correspond to gaps. So you can say, I have a data type, which is a vector, which has data, data, gap, gap, data, data. Okay. So this pattern is what we want. We want to receive into that pattern here, data, data, gap, gap. And in fact, all of them are like that. Data, data, gap, gap, data, data. Okay. So if we can define a strided pattern, which MPI calls a vector, or a more general concept as a subarray, but vectors we'll do here, which is block, gap, block, gap, block, gap. And that's what we want here, okay? So that's the first, okay? So what you would do is you would specify an MPI gather where the send count and the send type is not equal to the receive count and the receive type. The send count is 4 and the send type is integers, but the receive count is 1 and the receive type is, I would call this a vector 2 by 2, this object here. So you might be worried here. You might think, surely in MPI, the send count and the send type and the receive type need to be the same. Well, that's not true if you use derived data types. So when you use derived data types, in this case vectors, you can send 4 integers and receive 1 vector, and well, it will, so Thomas, that's exactly the problem. So this is the first problem. You've identified the second problem, yeah? So you've already identified the second problem, yeah? So that's exactly the problem, but that's the second problem. So you've identified the problem here, yeah? So the first step is to receive in the correct pattern. So this is a valid thing to do. Specify send count equals 4, send type equals MPI int, and receive count equals 1, receive type is vector 2 by 2. And that will work because these are compatible. Okay. However, so this is the required pattern. Okay, we want the offset of this to be 0 times. So we want to do, these are the vectors, we want to receive them like this. So the offsets should be 0 times size of int, 2 times size of int, 8 times size of int, 10 times size of int. Okay, we have two problems here. Okay, first of all, these aren't a regular pattern, they're 0, 2, 8, and 10. That's the first problem. And the second problem is we want to offset this second data type from rank 1 by 2 times. We want to offset it by a small amount. We don't want to offset it by, I don't know how big you think this data type is, but it's actually, so MPI actually defines the extent of this data type as being 6 from the start to the end. We want to offset it by 2. So we have two problems. A, the offsets in the receive buffer aren't regular, and B, the offsets are not multiples of the size of the incoming of the received data type. So MPI gather will not help us. So the first thing we have to use is the displacement of the receive buffer are not regular. We need to use something called MPI gather V. So MPI gather V isn't more general than gather. It takes vectors, i.e. arrays, for receive counts and displacements. Now for us, the receive counts are all 1, but the displacements, MPI gather assumes the receive counts are 1, 1, 1, and the displacements are 0, 1, 2, and 3. We can specify we can specify different displacements. So that allows us to specify the fact that the displacements here are not regular. They're 0, 2, 8, and 10. That's fine. The problem also, though, is that what is the extent of this object? Well, the extent is the distance from the start of the first to the end of the last element. MPI type gets is 6 integers. So MPI says this thing is 6 integers long. So if I say MPI gather says displacement is always in size of object. So if I say displacement equals 1, that will receive it at 6. And this is exactly what you would get. This is exactly what Thomas said. You would get this problem that you would get the first, they wouldn't be interleaved. So the second thing you have to do is you have to trick MPI and tell it to redefine the displacement of the data type. So there are two tricks which you typically use to getting collectives to work correctly with derived data types. 3 tricks, sorry. One is send type and receive type don't need to be the same. You can send contiguous data and receive strided data, or the other way around. You just have to make sure that if your send message contains 4 integers, so does the receive one, but the displacements don't matter. The second one is you need to use a general collective which allows you to specify different displacements, which is typically a V alternative. There's gather V, there's all to all V. And the third one is you have to lie about the extent of the data type. It's all a bit nasty. The solution is to resize the data type. So we resize the new, so it has a more useful extent. I would think the useful thing is call it 1 integer. It's a really nasty routine on MPI type create resize. You give it the old type, you get back a new type. You tell it what the extent is, which is of type MPI A int. This is because this could be a byte address. You can also specify where it starts. You can tell it to start not at the origin, but we're not going to use that functionality. So you can both tell it to start not at the origin and to have a funny extent, but we're not going to use all that functionality. So it's really rather nasty, but it is worth it. And I did debate whether to give this lecture. I appreciate it's very technical, but it is very useful because it allows you to exploit collective routines in real situations. So we resize the lower bound specified for the data type starts. We can create a leading gap, but we don't need that. We're happy with LB with equals 0. And these are technically 64-bit types, which is rather nasty. But the way I'm going to do it is I say MPI int C, I declare int lower bound, int size, and LB all 0. Okay. I query the extent. I'm being clever here. I could use size of MPI int. So yeah, I'll come back to that, Luca. That's correct. I'll come back to that. That's a very good point. I get the extent, which is the int size. I say I want to create resize. This is the old thing, vector 2 by 2. I want it to have lower bound 0. I want it to be the size of an integer now, and I get this thing called vec resize back, and I have to commit that vector type. So that's all a bit horrible, but it basically gives me a data type which has the correct, I've called it vec because it has the correct size. Now, Lucas said the subarray derived type does not already handle it. It does, but it's a slight technicality that if we were to use subarrays for gather, yeah, we would need on the receive side a different data type for all the incoming ranks. We need a yellow data type, a green data type, and a red data type. And the gather doesn't allow that. It only has one receive type, not multiples. So what we have to do is use the same receive type as a vector, but use different offsets. If there were a gather operation which had multiple receive types, then you could do that, but we can't here. It's a bit of a technicality, but you're absolutely right. You're absolutely right. The subarray data does handle the offset, but unfortunately we can't use it for gather. It's like it all gets rather technical, but that's true. Okay, so what we do is we create a vec resize. So actually, for all-to-all, there is a version called I maybe should mention that. For the all-to-all routine, there is actually a version called all-to-all W, which allows you to specify multiple data types as well. And in that case, you can do the general case. So actually, for 3D halo swaps in general, you need to use something called all-to-all W, because you need to specify multiple data types, because the data types in the X direction might be contiguous, the Y direction might be are different subsets. So actually, there is a slight subtlety here I haven't talked about. I'll maybe mention that later on. I think I mentioned that at the end. So if I do MPI gather is send buff, send count, send type, receive buff, receive counts, displacements, receive type, root com. I say send count is 4, send type is MPI int. I say receive counts is 1, 1, 1, but the displacements are 0, 2, 8, and 10, and the receive type is vec resize. It will then do the right thing. So you have to do a lot of setup and head scratching and drawing lots of diagrams, but once you've done it, you can just call MPI gather v and it does the right thing. Now, gather v is rarely a performance hotspot. You tend to do it at the end of the program, but this generalizes to things like all-to-all and neighborhood all-to-all, which are often at the core of a. Now you could get around all this by doing explicit copy in, copy out. You could rearrange the data, but that's a hassle. Well, they're both a hassle, but I think this is probably the right thing to do. So other collectives. So the similar tricks can be used for scatter. MPI all gather and all scatter also have vector versions. So many scientific applications use the all-to-all pattern. This is for global vector transposes, but actually the neighborhood all-to-all is also can do halo swapping. The vector version all-to-all v plus derived data can ensure all data is up and directly in the correct place, avoids the copy in, copy out. The problem is all-to-all v has a single send type and a receive type, but the vectors for send vectors for send counts and set displacements. There's only one data type. So all-to-all v has a single send type and receive type, but vectors for send counts and displacements as well as receive counts and displacements. But it has a single send type and receive type, and that's not general enough. So all-to-all is default. All-to-all v takes a vector, then they had to invent another one, so they just picked the next letter of the alphabet called all-to-all w. So there's an even more general form all-to-all w exists. You have vectors for send types and receive types as well as counts and displacements. So I think this would do what Luca wants. You can have multiple data types. Okay. In this case, though, there's no obvious displacements. There's no obvious. They just gave up here and say all-to-all w uses byte displacements. So actually, for all-to-all w, you don't need to worry about resizing things, because you specify the displacements in bytes, not counts, not size of object. So it's a bit disgusting, but actually it does simplify things. So Luca, so basically all-to-all W is probably the routine which people most often use, and it would allow you to specify an array of derived types, which could be subarrays. And actually, then you would need to use, or you could specify all displacements as 0. You could specify all your byte displacements as 0. That would actually be quite elegant. I haven't thought about that before. Does that sort of answer your question? I'm kind of skimming over this a bit, but it is a bit technical, but I think it is an important thing to understand. Yeah, so it's a bit, apologies for this, but I really wanted to I think really, I think the main thing to understand is, if I go back a bit, is that the default gather does this. It receives things in rank order contiguously. That is normally not what you want, okay? So, you know, if I had, you know, I want to do more complicated things, I need to do scattered patterns, and that would be true for halo swapping. I want to do something more like this, okay? And there are ways of solving that. If you use the gather V version, where you can also specify a single data type, you need to play around with, you have to hoodwink MPI into the size of the data type so they all line up correctly. If you use the W, there isn't a gather W for strange reasons, I don't know why. If you use the W version where you specify the displacements in bytes, then you can get away with specifying them all precisely. So, so summary, technicalities are very complicated. You may have to play tricks with extents to the collector's work if you expected. However, I think it's worth the effort. MPI collectors are very highly optimized. I mean, if you do a naive DIY implementation, you will send P messages on P processes. Optimized collectors should scale as log 2P. And even on 1,000 processes, log 2 of 1,000 is 10, because 2 to the 10 is 1,024. So you're talking about, you know, this isn't a bit quicker. This isn't twice as quick. This is potentially 100 times faster on as few as 1,000 processes. So you can do copy in, copy out. You could rearrange your data into the correct pattern, do the all-to-all, and then unpack it at the other end. But derived data types in collectives avoid this ugly copy in, copy out. It is a bit of playing around, a bit of nastiness, and you need to understand what's going on. But once you've done that, the rearrangement of data is done automatically by MPI. You have a single call to MPI all-to-all V or W, and that's used by many parallel scientific applications. And so if you really wanted to use MPI neighbor all-to-all to do halo swapping in something like a 3D grid code, you would need to use MPI all-to-all V or probably MPI all-to-all W. I have actually used MPI neighbor all-to-all W, I think, for doing halo swapping in an unstructured code, a finite element, not even a structured code, unstructured finite element code with a graph topology. So it does work if you can get all your ducks lined up in order. So the exercise is, as I said, we're running quite late. No, we're running quite late, but we're finishing at 5. There's not enough time. If you're interested, I will just show you how the exercise works. So I'll share this different window. So if I so this is my, you should be able to see my, yeah, we can see my window there. So what I'm going to do, I'm just going to cut and paste the so you see it's I've distributed this slightly as a tar file. I can just, though you get it there. And so what I've done is here, there is the first exercise, there's MPI gather and gather 2D. So what I'm going to do is MPI gather Okay. The exercise is in a comment at the top. So it's a slightly simpler example. We've got a cyclic distribution. So rank 0 has elements 0, 3, 6, 9. Rank 1 has 1, 4, 7, 10. Rank 2 has 2, 5, 8, 11. We want to bring them back in this order. So it's very similar to the 2D exercise, but not quite as complicated. Without using MPI data types you've received in this order, we want to receive in this order. So you just use a vector data received side, and this requires the data type to be both defined and resized properly. But you don't need you can use an MPI gather. You don't need the gather V, because the displacements are, if you look at it, the displacements are regular. The complication about the 2D example is the displacements are not regular. They're in 2D there, and so that's in the MPI gather 2D.c exercise, where I've a matrix here, and I'm saying I want. So that's what I want to do here, and I think this prints the. It's a very simple code written with quite simply with. There's a Fortran version as well. I've just picked some parameters here. So there are solutions to that, which are actually, I'll just give me a second. I realize I don't have my normal. Yes, I prefer it if it's white. I don't like the coloring; it makes it hard to see. I think sometimes on the screen. You are seeing that? Yeah, fine. So there's also so there is, for example, a solution there. Sol.c, which is a solution. Shows you what to do, and it does the naive thing. MPI gather, prints out the matrix, and then does it correctly using gather V with a vector, and does it. There's Fortran versions, they're just the same, I think. Yeah, just the same. Fortran. If you're interested in here, there's also two. There's user defined.c, which tells you how to. So if you've done the MPI course, you'll remember that one of the exercises is to send a compound data type. So it's a compound data which has an integer followed by a double. So what you have to do is you have to define a structure derived data type, so you can send and receive that as a single object. But what we want to do is actually to add it up. And so this illustrates how in MPI you can register your own user-defined functions for collective operations. So what you have to do is it's a bit of a long-winded thing, but okay, here's my structure. Okay, I have to write a function which adds these, and I call it what it wants. So I call it some compound. It has to have this prototype. Has an input vector, an input-output vector, a length, and a data type. And so I have to say, it has to loop over all the elements and add them. And of course, I just add them. To add these two things together, I add the integers together, and I add the doubles together. So I have to write a function which adds these objects together, and it has to have a specific prototype. Having done that, I have to register it with MPI. So if you're, I have to, first of all, I have to create the data type with MPI type create struct, but I also have to register the operation. And so where I do that is it's called MPI opt create, and I can't see where it is now. I have to say to MPI, okay, I've written this function which I want to use in a reduction operation. I called it sum compound. That's what the function was called. But I want you to register it and call it MPI compound sum. And this one here is whether the operation is commutative or not. And addition does commute, so that one is true. But basically, I can then call MPI or reduce on these variables here, which are structures, which MPI knows nothing about because I've defined them, but I can call it with my own operation, MPI compound sum. If I call the MPI or reduce on these structures with MPI sum, MPI would say MPI sum is not valid for that data type. So again, it's a bit complicated, but it can be useful to be able to register, again, derived data, reduction operations are so heavily optimized, it's worth using them whenever you can. Some people say, well, MPI or reduce only works on doubles or integers. I have my own derived types I want to use. Well, you can, if you jump through a few hoops, get MPI to run collective operations on your derived types. You just have to write a function which does what you want to do and register it with MPI. And that's cool. So the predefined ones were MPI sum, MPI max, MPI min. I've just created a new one here called MPI compound sum, which is my own one. So that's the philosophy. So I thought I would leave that in there. And there's a more complicated one called merge sort list, which is just really there for fun. But so, I mean, so that I thought I'd give you the code and the solution so you can see how it works. And the utility of this is probably illustrated most in using them for 3D neighbor swaps with using all to all W, which would be rather too complicated to show here, but the philosophy is the same. So that's really the end of the lectures for today. Well, it is the end of the lecture for today. I'll be around for at least the next quarter of an hour. I will